Anyway, so thanks a lot for having me. We're going to switch gears a little bit. We're going to talk about legged robotics. That's what I mostly work with in my research. And we show you a little bit on how we are embodying intelligence in these types of vehicles, mainly through like learning from experience while having them in the field to make the systems literally walk across an arbitrary terrain. So this video illustrates a little bit on what these machines can do. You see them walking across different types of terrain, issues they had to deal with, sliding, slipping grounds, you have obstacles on the way, you might have muddy terrain, and the robot has to somehow have a way to overcome all of these things. Now, if you look at this problem in a very classical way and how people would address this, is that you're setting up kind of a multi-level control problem. On the very high level, you have kind of a navigation algorithm that tells us where the system can walk through. Then you have a local motion planner that figures out where the robot can step, how it should move the base. On a third level, you then figure out what is the actual joint level commands that I have to give in order to follow this motion plan. Then you execute this in a real system. We're talking here about kilohertz, update rates, hundreds of hertz and tens of hertz. Now, if you deploy this on the real world, you're going to face tons of different issues. First of all, questions like, what is the best way to move? What kind of gauge should you apply? What is the right stepping frequency? And also the real world is really full of corner cases that require the robot to adapt. You may have external disturbances that you have to observe and react accordingly. You have to detect how the system, whether the system is slipping or not, and you have to trigger recovering reflexes for that. You might bump into something and you have to trigger height reflexes. And all of that, if you want to integrate this in this classical approach, typically requires all kinds of different handcrafted heuristics that people embed. And the more complex the problems become, and this is once you go to the real world, the more of a tuning you need, the more of heuristics you have to embed. And the question is also for us a little bit in what is actually the right sensing that we need for these robots of the environment in order to make them move around. And what we have been working on in the last couple of years was mainly about couldn't we make the robot to learn all of this on its own instead of like us figuring out what are the right reflexes that they have to take. And the direction that we're following here is using reinforcement learning. I don't have to tell you about how all of that works, but what we're doing in essence is that we're creating tons of data in simulations where we try to replicate as accurate as possible the actual physical system in a digital world and let it generate data while becoming better and better. So I have here kind of a world that is of increasing complexity. It's like if you play a game, the better you become, the more levels you achieve, the harder the levels become. And the same thing that we're trying to replicate here for the robots. And after like some tens of minutes with simulating thousands of robots in parallel, we're able to make them move across challenging environments, as you can see here in this short video. Now, the question is, how do we transfer this now to the actual real system? And there's two tricks that we apply here. First one is that you have to somehow cover these problems of the robot not being exactly modeled in the simulation. On one side, you're changing this rigid body dynamics, so you're changing the masses, the link length and stuff like that, and some to robustify all of that. And the second big thing is that we go on the actual physical system, we generate data on the physical system, and we bring back this data, for example, to replicate what is the actuator performance, what are the actuator limits into our reinforcement learning loop in the simulation in order to have a much more accurate representation of the actual physics. The second thing, and this is a lot more important, is how do we actually handle these kinds of challenging terrains that you're facing in the real world? We're going to have robots that can move across snow, rubble pistes, and whatever. And it's actually very hard for us to simulate these kind of things. And I think even if we could, it's then hard to sense on the actual system. And lastly, even if we could do everything imperfect, the question is really, what is the important information that the robot has to extract from the environment in order to move appropriately? And what we did here is that we applied a method called privileged training. In the first step, what we're doing is we're generating a teacher policy, which in essence does the same reinforcement learning we have seen before. So you have a reinforcement learning algorithm that optimizes locomotion control policy. And now we're giving in a lot of privileged information. So information that might be useful for the locomotion, but we don't know yet. And for sure, we know that the robot might not have access to it. So this is like contact information, this is contact forces, this is exact terrain profiles, friction coefficients and stuff like that. And we encode this in some latent information. And the second step, what we're doing is that we're teaching a student policy, which has pretty much the same controller, and it tries to imitate the same output action. But what we're doing is, instead of figuring out this latent information from the privileged information, we're trying to infer that from experience while interacting with the environment. And the nice thing is that with this setup, we have now a principled way in how we can play around with, like, what is the right information that we have to give the robot? Do we need to give it haptic sensing or not? Where do we need haptic sensing in order to make the system move as it's supposed to move? On top of that, we then do again like this adaptive curriculum. So we do different types of terrains, different types of challenges that it might faces. And the better the robot becomes, the more challenging you make the environment. And obviously you cannot simulate all kinds of different terrains, but somehow the real world is kind of a mixture of all these different things of what the robot has seen in the simulation. It turns out that the transfer to the actual real world deployment works out very, very smoothly. I'm going to show you two research highlights out of that. So what you have here is the robot walking across flat ground, and we have here a wet whiteboard on the ground. The robot can't see this, so it looks exactly the same in the 3D perception, and see what the robot is doing. The robot steps on it, it immediately reacts to that, it stiffens up, it changes the frequency in how it's stepping, and all of that without us telling the robot to do these things. So we looked a little bit under the hood and what is happening actually in the neural network. What kind of information does the robot encode? And if you decode that and you want to figure out what is the robot's interpretation of the friction coefficient of its environment, something that it cannot really measure from its perception data, you see that at the beginning, the assumption is it's a very high friction coefficient. Once I'm stepping on something, it immediately drops. And then after leaving this wet surface again, you slowly start to gain confidence and you increase again this assumption or this estimated friction coefficient. And it's actually astonishingly similar to us moving in the winter. If you're stepping on something that's slippery, you stiffen up, you react to that, and then you slowly gain confidence again and you adapt the behavior to move as normal. Here's a second experiment. We blindfold the robot and we put an obstacle in front of the machine. And that's what the robot is doing. So the robot moves, has no assumption about obstacles being in the way. It hits the obstacles, and now it memorizes this and triggers kind of a stepping reflex in order to overcome it. And again, if you look under the hood and what the network is actually doing, you see that you have, in the beginning while moving, you have a certain uncertainty about what is the height in front of the robot, but you assume this to be kind of similar to what you have been seeing before. As soon as you hit something, you're going to adapt this assumption about where this environment might be, because you now realize that there is an obstacle in front of you. And again, once you're stepping on it, you slowly gain confidence that this is now the stepping height and you can move across it. And also, if you look at the saliency map, so the sensitivity of what I'm doing now based on sensor signal I've seen before, you see actually that this first collision that we had a second ago, this really still influences the motion I'm executing right now on my system. With this, I'm closing here. I hope I gave you a small glimpse in how we try to embed intelligence in our system. Thanks a lot.
Thank you so much. That was a really exciting presentation to see all the fantastic word coding. I was just wondering if you had any comment on how does the body, or if you change the physical structure of your robots, how does that change? Can you optimize the information gain so it can learn faster or quicker? Or if you take a learn policy and then adapt the body, how does that affect the robot's behavior?
So obviously the mechanical implementation of the whole thing has a lot of influence in how the system is moving. And you actually see this once you implement a different embodiment in the simulation and figure out what is now the optimal way in how the system is supposed to be moving given that model. You see a different type of behavior, how the system is moving. And you can now use this also in the reversed order. So let's assume you want to move with a certain velocity or achieve a certain goal. What is now the right topology, the right setup, the right infrastructure that you need as a robot in order to move like this.
I think it's really interesting how the body changes, affects the learning process. So thank you so much, Marco. And again, we'll have you back in a second for the panel discussion.